So hello guys, welcome back to my channel, and in this video I would like to solve an interesting Putnam series problem, and it's one of the shorter and the easier Putnam problems. Again, I don't know, again easy hard is all subjective. So let's get started, and you'll see for yourself what the problem is. Okay, so the problem goes this way. Say we have some given conditions. Given a1 a2 is equal to 1, and a2 times a3 is equal to 2, and a3 times a4 is equal to 3, and so on. And we also know that the limit as n tends to infinity of a sub n divided by a sub n plus 1 is equal to 1. So how do we tackle this problem now, because we have to find the absolute value of a sub 1. So this problem just wants us to reconstruct the entire series, or have like a general expression for say the a sub nth term, or a sub n plus 1th term, or something like that. So let's look at this first condition here. So if a1 times a2 is equal to 1, a2 times a3 is equal to 2, so we can generally an times a sub n plus 1 is equal to n, right? Because you can check for all the cases. It's basically equal to the index of this preceding term of a sub n plus 1. Fair enough. So this means a sub n plus 1 is equal to n divided by a sub n, and then we can do a similar treatment for a sub n also. So a sub n minus 1 times a sub n is equal to n minus 1, because this is holding true for two consecutive values of this sequence. So a sub n can be substituted as a n minus 1 divided by a sub n minus 1. So let's plug that here. In the place of a sub n, we have n divided by n minus 1 divided by a sub n minus 1, which can be rewritten as a sub n plus 1 is equal to, this will go on top, so we have n times n divided by actually n minus 1 times a sub n minus 1 in the numerator. Well, fair enough. We can do a similar thing like we did for a sub n for a sub n minus 1. So notice that a sub n minus 2 times a sub n minus 1 should be equal to n minus 2 by our condition. So a sub n minus 1 is equal to n minus 2 divided by a sub n minus 2. We can substitute that in, so we have n plus 1 is equal to n times n minus 2 divided by n minus 1, and in the denominator a sub n minus 2, and we can keep doing this for a sub n minus k, where k is an integer. We can keep doing this, and the pattern that we want to generate, that we are going to generate, is notice that when n gets subtracted by some even number, that goes in the numerator. So in general this pattern is going to look like n minus 0. You can consider 0 to be even, although it's a debatable question, but n minus 0 times n minus 2 times n minus 4, so n minus even, n minus 6, and this goes on, divided by, because we don't know the last term, right? The last term is a sub 1, which we need to find, but we don't know after how many n's, or we have a general n, so we need to keep the generality. We can't just terminate it and like assume that n was even, in which case a sub 1 would be in the denominator or something, or it's actually depends on whether n is even or odd, whether we'll have a 1 in the numerator or in the denominator, the a sub 1 term. So anyways, and n minus an odd integer is in the denominator, so n minus 1, n minus 3, n minus 5, and that goes again. We don't know if n is even or odd, because again, as if say n is even, then a sub 1 will go in the denominator. If n is odd, then a sub 1 will go in the numerator. So let's write this as an infinity, as a limit, basically tending to infinity. So we can see the limit as some dummy variable, in this case goes to infinity, of n times n minus 2 times n minus 4 dot 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 till some n minus 2k divided by n minus 1 times n minus 3 times n minus 5 dot 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 n minus k. And this perfectly fits with our pattern that we have: even n minus some even integer in the numerator, n minus some odd integer in the denominator. Fair enough, that's the general expression for a sub n plus 1, and believe me, there is a way cleaner way of writing this. So a sub n plus 1 can be written as, notice that we have n minus 2 and then n minus 4, so there is a skipping of 2 in consecutive terms. So if this was 6, we have 6 times 6 minus 2, so 6 times 4, we skip the 3, so there's a jump of 2. So 6 minus 2 is 4, minus 2 is 2, so there's a jump of 2, and it's not entirely a factorial, but it's a jump of 2 type of special factorial, which we call it the double factorial. So this, look at the starting term n, is going to be n double factorial, because we assume that this ends in 1, or an irreducible number. And in the denominator, this is, take the first term, again skips of 2, so taking the first term, n minus 1 double factorial. So that's a nice compact expression we have for the n plus 1th term of this sequence. But believe me, this form is not going to look pretty, so we need to condensify, we need to simplify this further. And I'm not only going to simplify this double factorial, I'm going to do a simplification for a general simplification for multiple factorials. Here we had skips of 2. What if we had skips of, say, alpha, say n minus alpha, and then n minus 2 alpha the next term, and so on. So see you on a fresh page. Now for the multiple factorial, take a general case, say n multifactorial with, say, alpha skips. We write this is the right notation. So this basically denotes that we have n times n minus alpha times again a subtraction of alpha from this previous term. So n minus alpha is n minus 2 alpha, and that basically goes on till alpha plus 1, because we are considering n to be 1 more than uh, the nearest multiple of alpha. So n can basically be represented as k alpha plus 1, where k is another integer, can be any integer. That's what a multiple, one more than a multiple means by definition. So eventually, if you go reducing n by alphas as per this multiple factorial of alpha jumps, if if you take this multiple factorial, the special number k times, or say in this case say k minus 1 times, say you take this infinite this multiple factorial k minus 1 times. So you're going to subtract with k minus 1 times alpha. So you're going to be left with, well, the k alphas are going to cancel out and we have just the alpha and this 1. So you're going to anyways end up with alpha plus 1, and then if you reduce alpha plus 1 again with an alpha, you end up with 1, and you know that's where you end the multiple factorial. Okay, so if we have something like this, we can basically do a lot of factoring out over here. So n multiple factorial of alpha jumps is n times n minus alpha dot 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 alpha plus 1. Then we can take out an alpha from all of these fractions. So you have alpha raised to the n minus 1 over alpha power. And why is that? I'll explain. So basically notice that any term of this multiple factorial can be represented as n minus t minus 1 alpha, where t is the number of which term it is. Because if you plug in again t equals 1 or the first term, you just end this alpha factor cancels out, you end up with 1. And then for the second term, when you plug in t equals 2, you end up with 2 minus 1, which is 1 times alpha. So n minus alpha, you have the second term. So this is general term for this multiple factorial. We want this equal to alpha plus 1 to actually see how many terms there are in this multiple factorial up to alpha plus 1. So and we need to make t the subject of the equation to find what number of term that is. So when I do that, I have basically n minus 1 and alpha plus t minus 1 times alpha. So this plus alpha and this minus alpha are going to cancel out nicely. And we just have an alpha t. Alpha t is equal to n minus 1, making t the subject of the equation with n minus 1 divided by alpha. So there are n minus 1 divided by alpha terms in this multiple factorial that we've represented. So if we want to factor out an alpha from all the terms, we need to raise alpha to the n minus 1 over alpha power. And since we do that, we have to divide by alpha in all the terms, right? Because we can't just multiply it by this separate factor. We need to maintain equality that way. So this becomes n over alpha. We are dividing all the terms by alpha because we factored that out. N minus alpha over alpha till alpha plus 1 divided by alpha. Okay, so let's simplify this over. We alpha raised to n minus 1 over alpha. This is n over alpha. And we have over here n over alpha minus 1. And eventually we end up with 1 over alpha plus 1. And this can be represented in terms of, well, gamma functions, to be more specific, because this is a fraction, right? Writing fraction factorials is just bad news because fractions wouldn't necessarily be result in integers. What if you have 1 over 3 or something like that? It's going to be real weird to have the factorial of that. So the gamma, we can write this product because again this is a factorial, right? N over alpha times n over alpha minus 1 times n over alpha minus 2. So this can be written as n over alpha factorial. If we want to generalize and write in terms of gamma, is that factorial term plus 1. So n over alpha factorial, right? So this is gamma of n over alpha plus 1. But we also need to divide by this stopping term because according to this gamma of n over alpha plus 1, this means that you are going with this multiplication until 1, but in reality we are stopping at this 1 over alpha plus 1. So we don't want the terms after this 1 over alpha plus 1, because the gamma in itself doesn't know when to stop. So we need to divide by those excess of terms that are there after 1 over alpha plus 1. So we need to divide by 1 over alpha plus 1, which is basically 1 over alpha factorial, because 1 over alpha factorial is basically what's after this 1 over alpha plus 1. But 1 over alpha factorial is gamma of 1 over alpha plus 1. Just this factorial term plus 1. And there we have this general representation of multiple factorial of alpha jumps. And without losing generality, we originally had n, which was 1 more than the nearest multiple of alpha. We can extend this to most other n's. So there we have it, a perfect treatment of multiple factorials. But in our case, it was a double factorial, so alpha was 2. So n double factorial is basically 2 to the n minus 1 divided by 2 times the gamma of, n over 2 plus 1 divided by gamma of 1 over 2 plus 1. And yes, we have a nice generalization for the multiple factorial. Now it's actually time to use this definition back into our a sub n plus 1 term. So let's do that on a fresh page. So previously we obtained that our a sub n plus 1 term could be represented as n double factorial divided by n minus 1 double factorial. But we found a nice formula for a double factorial, right? Which was basically 2 to the n minus 1 over 2th power times the gamma of n over 2 plus 1 divided by the gamma of half plus 1. So we just need to modify n's in all these cases that we are going to deal with. So for n factorial, just copy this as it is, 2 to the n minus 1 over 2 times gamma of n over 2 plus 1 divided by gamma of half plus 1, and this is itself divided by n minus 1 double factorial. So in place of n, substitute n minus 1. So we have 2 to the n minus 1 minus 1 is n minus 2 over 2 times the gamma of n minus 1 over 2 plus 1 divided by the gamma of half plus 1, because the denominator is independent of n. So notice that these denominators are cancelling out nicely. So we have basically 2 to the n minus 1 over 2 divided by 2 to the n minus 2 over 2 times the gamma of n over 2 plus 1 divided by the gamma of n over 2 minus half plus 1. But we can do one quick simplification on our part. So we have n minus 1 over 2 in the power of 2 divided by 2 to the n minus 1 over 2, and along with a minus 1 over 2 that's being added, which we can basically separate into another power of 2 by the properties of exponents, and then the gammas are remaining the same. So gamma of n over 2 plus 1 divided by the gamma of 1 minus half is half, so n over 2 plus 1 half. And notice that these terms are cancelling out nicely because these can't ever be 0, so we are safe there. This 2 to the negative half power can be taken up, and 2 to the half is square root of 2 times the gamma of n over 2 plus 1 divided by the gamma of n over 2 plus half, and this is nothing but our a sub n plus 1th term. But we have to find a sub 1, right? It's simple now. Just take, rather plug in n equals 0. So 0 plus 1 is 1. So a sub 1 is going to equal square root of 2 as it is, gamma of 0 plus 1, 0 by 2 is 0, divided by gamma of 0 plus 1 half, which can be simplified to half, square root of 2 times the gamma of 1 divided by the gamma of half. Well, this is nothing but 0 factorial, right? Which by definition is 1. And we have square root of 2 outside. And well, the gamma of half, I've made a bunch of videos relating the Gaussian integral to the gamma function. So the gamma of half is the entire Gaussian integral, is just square root of pi. So that means a sub 1 is nothing but square root of 2 over pi if you take everything under a common root. And what were they telling us to find again? A sub 1, but the absolute value. Since this is positive, we don't need to bother for this sign change. This is just going to remain square root of 2 over pi. And that's how we solve a Putnam sequence problem. I hope you really like this video, guys. It's a really quick and clever way of solving this problem. That's it for this video. So hey, please like, share and subscribe to my channel. Recommend me to your friends. Spread the word as much as possible. You can follow me on Instagram. I have this username gamma_digamma. And in the meantime, stay home, stay safe. Have a great day. Peace out.